Okay, so let's wait just a few more seconds and I'll get things started. You ready, Tamas?
Yes.
Okay, let's give it just a few more seconds. So, welcome everybody to the Western Hemisphere Colloquium on Geometry and Physics. We're going to start the talk in a moment. During the talk, please remain muted. If you have a question, the best way to get it to the speaker is to put it in the chat, address it to everybody, and I will aggregate the questions and present them to the speaker. After the talk, we'll have a question and answer session, and for that, the best way would be to use the raise hand feature and just remember to unmute yourself and ask the question. That'll be after the talk. Anyway, we're very happy to have today Tamas Hausel of IST Austria, and he suggested that he might start by telling us about IST. And he will be speaking, as you see in front of you, about mirror symmetry for Langlands dual Higgs bundles at the tip of the nilpotent cone. Tamas.
Thanks very much for the invitation as well, as to be able to speak here. Yes, I wanted to say a few words about IST Austria, or institution here in Vienna or close to Vienna. It's here behind me, so I am having this nostalgic picture of our working place because we of course haven't been there for a year or so. It is in the suburbs of not the suburbs, it's in the Vienna woods, 20 minutes away from Vienna. And it's a PhD granting institution in the basic sciences, Institute for Science and Technology. Technology is in the future plans to use our. So we are slightly similar or based on the Weizmann Institute model. Also, somehow you can consider this Austria's answer to the Max Planck Institute, but it's all in one place, all the basic sciences. And we have PhD students and postdocs and professors. Okay, so that's about my workplace. And let me then talk about this new, well, this talk will be based on a recent paper with Nigel Hitchin. So the paper is more or less self-contained, so a lot of details are there. And today, instead of really talking about the paper, I will give you the pre-talk. I will give you some background, which is not really discussed in the paper, and then say mention a few results from the paper. But at the end, I want to finish with the conjecture, which somehow, funnily enough, it emerged after the paper was finished, because retrospectively, it looks like that the paper is super streamlined and it's very logical how it happens. But in practice, it wasn't like this. It's only at the end things got to put in place. Okay, so in the first part, I then recall some ideas about mirror symmetry for Higgs bundles. It will be pretty schematic, partly because some of the conjectures I will be mentioning, they are not really, what happened? Attempted to start. Do you see it, my screen?
We see your screen, yes.
But I think it's frozen.
It is frozen.
And what do we do now? Maybe I restart. Okay, I don't know what happened.
So we'll disconnect and reconnect?
Yes. Okay. But now you have to meet, this meeting is okay. You have to make me host again.
As soon as you reconnect, yes.
Sorry, I don't know what was this. Yes?
Yeah, I'm working on it. Oh. I only see one of you, and that one is already co-host.
No, I think this one is, there is also somewhere should be my iPad.
Got it.
Done. Okay. No.
Try again.
Okay, now of course, okay. Screen share. Screen. Start broadcast. Okay. Now let's go back to here. Okay, now hopefully this will be not happening again. Okay. So, right, so let me then just, again, as I mentioned, it will be schematic. I will use the language of general complex reductive groups. But I will, in fact, the main part of the paper, as well as in this talk, we will concentrate on GLN. So things will be simpler than in the general case. But it's just good to understand the abstract scenario with the general complex reductive group. So we have, again, a complex smooth projective curve of genus more than one. We have a complex reductive group, which you can think of as a complexification of a compact Lie group. These such groups are classified by some sort of root datum, and the root datum has a dual root datum naturally encoded into the structure. And to that root datum, there will be a dual group corresponding to. So at any rate, these complex reductive groups come in pairs, the so-called Langlands dual and the original group. So the examples which will appear, specific examples, will be GLN, which is self-dual, and SLN, whose dual is SLN modulo its center, which is the adjoint group of GLN, PGLN. Then we will be studying a moduli space of G Higgs bundles on the curve. I am usually thinking in terms of spaces, so I usually have a moduli space of semi-stable Higgs bundles, but often when we will formulate things, you will probably want to think about the stack instead of the space, the moduli space. So roughly speaking, a G Higgs bundle, the object in this moduli space, is a pair of a principal G bundle together with the so-called Higgs field, which is a section of the adjoint bundle tensored with the canonical bundle. So these pairs, then you can define stability conditions, for example, and you can construct a moduli space. And one of the amazing properties of this moduli space, that first of all, we will see it's hyperkähler, but in particular, it's holomorphically symplectic. And with respect to this holomorphic symplectic structure, there is a completely integrable Hamiltonian system on it, defined by the so-called Hitchin map, which is a map from our space to a vector space of half of the dimension. And then the functions these give will be commuting Hamiltonians. And the map will be proper. So in particular, we will get that the generic fibers are certain abelian varieties or compact tori topologically. Yes. And again, in order to really bring in the full story, we have to, we say, change complex structures on this manifold. So this other manifold, which is closely related to this one, is the moduli space of flat G connections on the curve. We denote this by M deram G. The previous one actually was denoted by M dolbo G. And there is a whole theory of them, and there is something called the non-abelian Hodge theorem, which identifies the manifolds underlying these algebraic varieties by a diffeomorphism, a canonical diffeomorphism. But another way to think about this non-abelian Hodge theorem is that it gives two complex structures in a natural hyperkähler structure on M Hitchin, which is a certain solution space to Hitchin's self-duality equations on a Riemann surface. So it's a hyperkähler manifold. It has a family of complex structures in quaternionic relation I, J, and K, and you have 3 Kähler forms with respect to the corresponding complex structures. So in this hyperkähler metric, in complex structure I is special. It corresponds to the complex structure given by the moduli space of Higgs bundles. And the other 2, J and K, are complex analytically isomorphic, and they are isomorphic to the complex structure given by the moduli space of flat connections. So that's these are our spaces. And now I will mention the 3 aspects of mirror symmetry for Higgs bundles, which will play a role for our considerations. So the first one, or the story for us, or for me, with Michael Tadeusz, started by noticing that the one version of mirror symmetry, the so-called Strominger-Yau-Zaslow mirror symmetry, which originally was for Calabi-Yau compact threefolds, are naturally present between the moduli space of flat connections for SLN and PGLN moduli spaces. Namely, what you have is the Hitchin map, which was defined using the complex structure of the Higgs moduli space complex structure, but you can as well consider it on the flat connection moduli space. Will turn those holomorphic Lagrangian fibers of the Hitchin map into special Lagrangian fibers, special Lagrangian tori, and they will be naturally dual special Lagrangian tori in the generic fibers, which was one of the requirements of the Strominger-Yau-Zaslow proposal for mirror symmetry. So this actually was then later proved for general reductive G by Donaghy and Pantem. So we now have this picture that for generic fibers of the Hitchin map, we have these dual abelian varieties, which then in the moduli space of flat connection complex structure turn into special Lagrangian tori. And that's why Strominger-Yau-Zaslow is by this theory actually is naturally there. So with Michael Tadeusz in 2002, we were wondering if we can come up with a mirror symmetry proposal which contains numbers, some numerical agreement on the 2 sides. So to show that there is really mirror symmetry happening between these 2 spaces. And we managed to come up with what can be called topological mirror symmetry. And this said that certain Hodge numbers of the moduli space of flat connections, SLN flat connections, agree with the Hodge numbers of certain Hodge numbers, again, of the moduli space of flat connections, but now for the Langlands dual group. So we had to find a pair of groups where these were different for topological mirror symmetry. Otherwise, there is nothing surprising can happen. But then we managed to do this. Here, really, one of the difficulty was really to find the right notion of Hodge numbers, partly because the varieties are non-compact. So these are open varieties, quasi-projective varieties, and partly because PGLN variety was an orbifold. But okay, we managed to do that. And then even already in the paper, we actually identified the Hodge numbers of the flat connection moduli space with the Higgs moduli space. And therefore it was enough, and that's what we checked in the paper for SL2 and SL3 to check the conjecture for the moduli space of Higgs bundles. And excitingly for me, there is now a proof of this conjecture by Michael Gröschenig and Dimitri Wyss and Paul Ziegler. The first 2 were my PhD students, and they use periodic integration along the Hitchin fibration to find a very pleasing and arithmetic proof, in fact, of the conjecture, which was arising from ideas from mathematical physics. And they went further and used the same machinery, but for general groups, not just SLN and PGLN, and they managed to reprove Ngo's main cohomological result, which proved the fundamental lemma. So that was, for me, as a really exciting development, and this really concluded, in some sense, these topological mirror symmetry questions, which we started to introduce with Michael back then. And the last one is somehow the full extent of the of this mirror symmetry, which is still pretty much open, is homological mirror symmetry. And which was, of course, for Calabi-Yau three-folds was suggested by Kontsevich, famously in '94, as a precise, more or less precise equivalence between two categories attached to the two Calabi-Yaus. And which became relevant in the story in the work of Kapustin-Witten in 2006, where they argued by physics arguments that the A model of the flat connection moduli space for group G should be equivalent with the B model of the flat connection moduli space for the Langlands dual group. And they argued that this is a consequence of S-duality from some in some four-dimensional super-Young-Mills theory. And this is the two-dimensional reduction of that symmetry. And then if you formulate then this conjecture, and roughly that's what they were doing in the language of Kontsevich, then this should be an equivalence between the Fukaya category of the flat connection moduli space for group G with the symplectic structure, the real symplectic structure of in that Kähler form, some sort of Fukaya category. In fact, it's still not precisely defined, definitely not in this case. On the other side, though, there is something which is well defined, is the derived category of coherent sheaves on the Langlands dual group with respect to the complex structure J. So, and then Kapustin-Witten makes an enormous journey starting from these ideas, and then they manage to explain the dream-fed Lamont-Bailins on geometric Langlands correspondence starting from these ideas. So that's really a lot of difficult things they managed to understand from a physics point of view. Then, or around then, it started around then, but then Donaghy and Pantev published the paper 2012. I already mentioned, they proved the general case of the Strominger-Yau-Zaslow picture, but they managed to also set up, because you have these generic, in this moduli space of Higgs bundle picture for Langlands dual groups, you have the two Hitchin maps, you have dual abelian varieties, and you can do Fourier-Mukai transform between them. You do it relatively against the Hitchin base, but you can do this generically when the fibers are abelian varieties. And they managed to prove this equivalence of categories between coherent sheaves, but over the generic locus. And the difficulty still today lies how to extend this over into the whole Higgs moduli space. So they call this the classical limit of S-duality. They argued that both of this category is a degeneration of this category, and this category is a degeneration of that category. But in fact, there is an overall picture which was advertised by Kapustin-Witten, whereby you can actually look at these categories which are seeing all the complex structures in the Hitchin moduli space. So you can think about branes, so these objects in these categories, which is type B with respect to complex structure I, and type A with respect to complex structure J and K. So this is some sort of symplectic object here, a Lagrangian, say, for the last two symplectic forms, but holomorphic with respect to the first one. And so that one of their suggestion was that the BAA branes should be mirror to BBB branes for the Langlands dual group. So a BBB brane, on the other hand, is some sort of sheaf kind of object which is holomorphic with respect to all the three complex structures. So mathematically, both of them can be understood nicely. So a very good example of a BAA brane is a holomorphic Lagrangian on the Higgs moduli space, where the Lagrangian property has to be with respect to the holomorphic symplectic form, which is a combination of the two real forms, two real symplectic forms. And so something holomorphically Lagrangian here will be Lagrangian in each individual complex symplectic structure omega j and omega k. And similarly, hyperholomorphic vector bundles were studied or are understood mathematically as, for example, some sort of vector bundle on the twistor space of the hyperkähler metric, something which is holomorphic with respect to all the three complex structures. And in this, here I have circled the first B's. So if you just concentrate, as I will do in this talk, on the first complex structure, you see that B model on the Higgs moduli space side should be matched up with the B model on the Higgs side on the other side. So in this extended version, but as I think Kapustin and Witten do say this, that the B model on the Higgs moduli space should be mirrored to the B model on the Higgs for the Langlands dual group. So in fact, it's part of the picture, not just the degeneration, how Donaghy and Pantev think about this, but just part of the picture. Also, what we will be looking at in all the branes will be either BAA, they will be either holomorphically Lagrangian, or their mirror then is going to be hyperholomorphic. So we are not going to leave this word. So I will be concentrating on the first complex structure, but in fact, this can be made sense in all the complex structures. So if there are any question now, or which may be interesting to ask.
Well, nobody's asked any question, but I could ask one if you want. Could you say something?
If there is no question, then it's everything is super clear.
Okay.
Yes, and if you see a good question, then I would be happy to hear it.
Well, maybe can you say a word about the effect of singularities of the moduli spaces? You're talking about hyperkähler rotations and manifolds. These are not quite.
Right. So that's I said that everything was very schematic, and part of the business is that, as I mentioned, there is issue that things have to be typically defined on the stack. There will be issues happening at the singular points of the. So it's now understood that even actually your conjecture here has to be modified probably. The singular points will cause to look at some different kind of sheaves, not just the derived categories. So there are many, many issues here which are now better understood. So here in your suggestion, for example, as far as I understand, you have to upgrade coherent sheaves with some particular non-trivial behavior around the singular points in the stable moduli space, or I don't know if you have to do, how do you deal with the stack? So there are many, many technical issues which make things hard. But you will see that what I will talk about, there everything will be simple and somehow we will get rid of these problems. So, but we will not have an equivalence of categories. We will just look at particular Lagrangians and we will be conjecturing or proving results about what we think should be their mirror. Okay.
No further questions.
Okay. So now this comes the little bit theoretical part, which I like to advertise, but it's also really the way how we think about the moduli space of Higgs bundles. So it has a canonical C star action. I will explain how, but such a C star action with the particular property will give us a partition of our variety into cells, into basically affine spaces, vector spaces, will cover the whole moduli space, and each of them will turn out to be a Lagrangian. So it feels like it's a basic construction. We have to understand this, the geometry of these Lagrangians, how they pave the whole space. So then this is in the framework of Bjelensky-Birula decomposition, first for a general semi-projective variety. So let me remind you of this notion of semi-projectivity. So we will take our variety, which you can think of as a Kähler manifold or a complex manifold even. But I like to think about smooth varieties, but until this paper, I definitely would insist on smooth things, but here in this paper, it looks like there are useful and important extensions of this idea, not just to the smooth case. But you should just think about the smooth case. But sometimes things will become singular. Also, in fact, things could become non-reduced, not normal, and even irreducible. There are lots of singularities can happen, and this notion still seems to be interesting. So we will call something semi-projective if it is endowed with a C-star action with the following properties. So the first one is that the C-star action have to be linear, which means that X has to C-star equivariantly embed into a projective space with a linear C-star action. So this happens every time X is quasi-projective and normal. Then you can lift the C-star action, linearize the C-star action on an ample line bundle. But in fact, what matters is this linear property. And then when, as I say, sometimes you want to go out of your normal world, you want to look at non-normal varieties, then, but this is the property you need, that the action is linear. Then you want the fixed point set to be compact, to be proper, which will imply that it is projective. In the smooth case, for example, this will be also smooth. And the final property, this attracting property, you want that you take the C-star orbit of any point on your semi-projective variety, and the lambda goes to 0, limit point, closure point should exist inside your space. So in one direction, you want to assure that you have always limit points. In the original theory of Bielanski-Birula, he has a projective variety, so he will have both directions and the limit will exist. But for us, we only require one direction exists, and in all examples, it will indeed be just one direction where it exists. So just let me give you examples to have in mind. You take the cotangent bundle of a smooth projective variety. That's a very good example of a semi-projective variety with the C-star action being the linear action along the fibers. Then you can look at the Higgs moduli space, as we will do in a moment, as another important example, but also Nakajima-Kuer varieties is an example. Was there a question or no?
No
okay,
question.
I just heard something. Okay, then what is also interesting for when I was preparing for this talk, that we actually expect Gaga principle in the smooth case for such semi-projective varieties. If you look at equivariant, C-star equivariant sheaves, C-star equivariant bundles, that category somehow is expected to be equivalent in the analytic and the algebraic category. And that's great because physicists usually have a hard time to think about algebraic stuff, but analytic stuff is fine. So if you like what I talk about, many things, you can just think it's analytic, complex analytic manifolds I'm talking about. Okay, so what are we going to do with these semi-projective varieties? We will be partitioning them into these upward flows. So what is an upward flow? The upward flow is a flow from a fixed point of the C-star action. So we take any fixed point of the C-star action. In the story, if it's non-smooth, then we're going to take a smooth point. Anyway, we should assume everything is smooth. Then we take the upward flow, which is the collection of points whose downward flow, the limit point, which we know should exist, is R point alpha. So we collect all those x's where this limit point is R alpha. This we will call the upward flow. Somehow you think of those points are the ones you can flow up from alpha, are the points where if you flow down, you reach alpha. Also, there is an analogous notion which probably not motivated. There's some sense Bielanski-Birula was aware of this relationship with dynamical systems. Smale called them stable manifolds, the analog of this construction for a dynamical system. And similarly, we can take the downward flow, the collection of those points, where now the limit point at the other end of the C-star orbit exists and agrees with or alpha. This will be another collection, and this will be the downward flow from that point, which bears the name unstable manifold in the dynamical system world. So what do we know about these flows? So the first main result of Bielanski-Birula, that these are cells. Each of the W alpha plus and W alpha minuses are isomorphic, locally closed subvarieties, and each isomorphic with a vector space, which we can in fact completely identify. It is going to be rid of the vector space from the tangent space at the fixed point alpha, which will carry a C star action, so we can look at the positive part of that C star module that will be T plus, and that vector space will be isomorphic with the upward flow from alpha, and this isomorphism will preserve the C star action. So we understand these things as a C star equivariant vector space identified with this infinitesimal model. So the semi-projective property, the fact that every point has a downward flow, says that the upward flows partition the whole space. Every point will flow down to somewhere, it will be in that flow. Again, we assume that the space is smooth. In that case, we can cover X with these upward flows. Now you can wonder, what can you do with the downward flows? I mean, you can still consider them. It will typically not give a partition of the whole space, unlike in the Bielanski-Birula story, where you get actually two Bielanski-Birula partitions. Here you just get some subspace, which turns out to be projective, and we call it the core of the semi-projective variety. So it's a good notion, I think. Of core, you should think of the zero section of the cotangent bundle as the core in that case. You will see in the Higgs moduli space, it's the nilpotent cone, or the reduced of that. And then another useful and important property of this core, even though it's projective, so it's nice in that sense, but otherwise it's a pretty crazy variety, very singular, reducible, many components, but it is a deformation retract of the whole space. And what will happen for us, that we will also have a holomorphic symplectic structure on our semi-projective variety of a particular kind, a kind where the C star action acts on the symplectic form in this homogeneity way. So the pullback by the action with lambda of the symplectic form will be just multiplication by lambda. In that case, and this is the case in all the three examples, the cotangent bundle, the Higgs moduli space, and the Nakajima-Quiver variety, there you have to choose the appropriate C star action for this property. In that case, you see that all the upward flows, as well as the core, they both will be Lagrangian. So one will give you a Lagrangian partition of the space. Lagrangian vector spaces will partition the space. And in the other one, you will get compact Lagrangians. Well, they only will partition you of this core. And they will have, therefore, the components of this core will be these Lagrangian components. They will be all equidimensional, for example. So now comes this notion of very stable, which you can make in this generality. So we will call an upward flow or a fixed point of the C star action very stable, if and only if the upward flow from that point or the upward flow itself has a trivial intersection with the core, with the union of the downward flows, namely it's alpha itself. What it means is that the upward flow, the stable manifold, does not intersect any downward flow, any unstable manifold from another fixed point of the C star action. And therefore, actually very stable accidentally makes also sense in this, this dynamical system language. And so the first theorem we prove is that this cell, this upward flow is very stable precisely when it is closed, subvariety in X. I mentioned they were locally closed, but if they are globally closed, then it is equivalent to be very stable. And to have another feeling about very stable, and this will be very nicely mirrored at the very end, we can define a partial order on the fixed point set of the C star action. So the partial order will be induced by saying that alpha is less than or equal to beta if either beta is in the upward flow from alpha, or equivalently alpha is, in the closure. In the closure of the upward flow from the other one. And this is going to generate a partial order. And in this partial ordering, you can see that very stable is precisely the maximal elements in this partial order. These are the ones which are somehow towards the top, or at least there is nothing above them in this partial order. Okay, so now let's use these ideas to study the moduli space of Higgs bundles, for which now I just quickly review some notions. So we will take, as before, a complex smooth projective curve, a Riemann surface of genus more than one, which was simplicity again, because also that's the language in the paper. We take just GLN for our group, the complexification of the unitary group. Then a Higgs bundle is just a pair of a vector, Rankine vector bundle this time, which is equivalent to the GLN principal bundle, and a Higgs field, which now the adjoint bundle is just the endomorphism bundle of E tensored with the canonical bundle. That's the section of that is called the Higgs field. So one can now define semi-stability and stability of Higgs bundles by the usual way you would do for vector bundles, except that you restrict your attention to subbundles, which are invariant by the Higgs field. And then you will have the same notion of slope semi-stability as usual. Then on the moduli space of Higgs bundles, as I mentioned, or we will be studying, or we will be interested in this canonical C star action, where C star acts by scalars just by scaling the Higgs field. So that's a C star action, and we will be studying it. So the first thing we can do is to look at the C star action in the light of the Hitchin map. So first, in this case, the Hitchin map is the easiest to understand. In this case, we just take the characteristic polynomial of the Higgs field, whose coefficients will be sections of powers of the canonical bundle. And so therefore the Hitchin map will take place in this vector space, which turns out to be half of the dimension of the whole space. So this Hitchin map is a proper map. It's one of the fundamental properties of it. And also it's a C star equivariant, T equivariant. If T acts on these components with weight 1, 2, etc., weight n, it's always positive weights, and if you have positive weights, then a vector space is itself always semi-projective. So A is semi-projective with respect to this direction because of the positive weights, and the core, if you like, is the origin, just the point. That's your downward union of downward flows. And just by general property, because it was a T equivariant one, you can also deduce that M is going to be semi-projective because the map was proper and T equivariant and the image was semi-projective. Every point in the Hitchin moduli space is going to have a C star orbit whose limit point will live inside the nilpotent cone, the fiber over 0. Additionally, the Hitchin map is a completely integrable Hamiltonian system. So that means in particular the fibers are Lagrangian, subvarieties themselves. Generic fiber is a Jacobian of a certain spectral curve you can attach to the generic characteristic polynomial. But the least of the least generic one, when A equals 0, when all these are 0, the Higgs field is nilpotent, is the collection, or in fact, it's not just a collection of the nilpotent Higgs bundles, but their scheme, the H inverse 0, we will think of as a subscheme of the Higgs moduli space, the scheme theoretical fiber of this map. And then you can take the reduced one. So this will typically be a complicated scheme. It will have, the components will have multiplicities, and then it's going to be, and in the paper we say a lot about these multiplicities, but not in this talk. I will probably not mention them. But then you can take the reduced, and then the reduced you can easily identify with the core of the semi-projective variety M, which you can actually, by the general story I started with, you see it's Lagrangian, but also Lomon in his paper in 1987, he proved that the whole nilpotent cone is Lagrangian. And you will see that he used this to say something about very stable bundles. But what are very stable bundles? First, actually, I don't go into that because it's in the paper, roughly the history. I already defined very stable Higgs bundles. So a Higgs bundles is very stable if and only if its upward flow is very stable, if and only if it has a trivial intersection with the nilpotent cone. There is only a single nilpotent Higgs bundle in the intersection, namely the bundle itself. A fixed point is always nilpotent. Or if and only if the upward flow is closed. So when the Higgs field is zero, that's your most trivial fixed point type for the C star action, then you are dealing with Higgs bundles of the form E0, where E, because the Higgs field doesn't give any extra condition, E itself has to be semi-stable. So you take the moduli space of semi-stable or stable, in the smooth case, Higgs bundles. And this is going to give you one of the components of the fixed points of the C star action. And in fact, it will live inside the core, and it will be one of the components of the core. It's itself Lagrangian, and the whole core, the whole nilpotent cone is Lagrangian, and therefore, because of dimensional reasons, the rest of the nilpotent cone cannot cover the whole stable bundle moduli space. That was Lomon's argument. Then there must be points inside here which are very stable. And then he used it. He was actually motivated by considerations of Drinfeld before. It has to do with the geometric Langlands and their way of thinking about the Langlands. So it's very natural from their perspective to look at very stable bundles. But here we extend the notion to look at very stable Higgs bundles as a generalization of the notion of a very stable bundle. And instead of discussing more the stable bundle moduli space, which is where the whole excitement lies, you have the geometric Langlands happening there, I would like to tell you in this talk that it's also interesting to look at this mirror symmetry picture at the top of the nilpotent cone, not in the bottom where this guy lives, but in the top. And in the top or at the tip of the nilpotent cone live these so-called type 111 fixed points. So let me just construct you such a fixed point, which I am going to talk about basically in the remainder of this talk. So we are going to construct a Higgs bundle, which will be maximally split. It will be the direct sum of line bundles. So we take n line bundles on the curve. We will take small little Higgs fields connecting them from mi-1 to mi times tensor k. So this is a homomorphism between line bundles. You can as well think of as a section of this homomorphism line bundle, but anyway, it's a section of a line bundle. And then it turns out that up to isomorphism, these Higgs fields, little Higgs fields, BIs, will be only determined up to scalar. So in fact, we can record the equivalence class and the scaling as the divisor of zeros of this BI. So you will get this DI, delta I, which will be the divisor, and because it's a section, it will be an effective divisor of zeros and non-negative linear combination of points on the curve. And to be harmonious with the rest of the world, we will actually encode M0 with another divisor, delta 0, but this time we will not assume delta 0 effective. It could be any divisor which represents the line bundle M0. Delta 0, again, is not completely well defined up to equivalence, up to principal divisors. It is well defined. So now we are going to take a vector of these divisors. The last n-1 of them will have to be effective. The first one is any. And I will construct from this data as a fixed point of the cis direction, a type 111 Higgs bundle. So the vector bundle itself is just the direct sum of these line bundles. The Higgs field will take values in that vector bundle tensor K, and this is only in the lower triangular form, just below the main diagonal. You have B1, B2, etc., Bn minus 1. These little connecting Higgs fields will give you this lower triangular Higgs bundle, Higgs field. So this pair of a vector bundle and the Higgs field is a very good example of a Higgs bundle, which typically, the underlying bundle, for example, will basically never be stable. But as a Higgs bundle, it could be stable. The condition is to take all fine invariant subbundles, but there are finitely many of them, finitely many subbundles, namely Mn minus 1 is in the kernel, but then the direct sum of Mn minus 1 plus Mn minus 2 and other invariant ones, and all these direct sum of line bundles from the end will be the subbundles. Now you have to compute their slopes, and you have to assure that the degrees are set up so that it's stable. So we will assume that this is stable. And some things at the end, probably we don't have to do that, but it's better because our notion of very stability makes sense inside the semi-stable moduli space, so it's better to assume they are stable. By the way, it is not true. So you can have, yeah, I mean, it's hard to, in the vector bundle case, Lomond proves that a very stable bundle, in the sense that something which doesn't have a nilpotent Higgs field is already stable, but something like this is not clear or not true for Higgs bundles. So we have to always assume that it is stable as well. So we assume it. And then what we do is that we characterize all very stable Higgs bundles of type 111. And instead of just being able to prove that they exist, we manage to completely characterize them. The theorem is that it is very stable if and only if the direct sum of the last n minus 1 of these effective divisors is a reduced divisor. So every point appears with coefficients either 0 or 1, nothing higher. In other words, the zeros of the BI, the little Higgs fields, are themselves single zeros, and they are distinct zeros among all the BIs. That's the condition to be very stable. And typically I don't include proofs, but now I want to sketch you our argument for this. So this was not for our first argument. So it now will sound very nice, but this one came after a lot of facts. But the proof will be very instructive for what will happen later and how I now think about these upward flows, that they are intimately related to these Hecke transformations. So the Hecke transformation, the simplest kind of Hecke transformations we will be looking at, these are the classical ones. People classically have studied them. So let me tell you, how do you make a Hecke transformation of a Higgs bundle at a point of the curve C? So we fix a point in the curve. We will take one of the fundamental Hecke transformations. They are labeled by basically by the fundamental weights, but for GLN it's slightly more complicated because you have the determinant as well. But anyway, roughly speaking, they are the fundamental representations. And we will take for K between 0 and n minus 1, K-dimensional subspace at the fiber of the vector bundle at the point C, such one which is invariant by the Higgs field at that point. So that's an assumption, an extra assumption. Usually when you do Hecke transformation of a vector bundle, you don't have additional assumption. Here you need an additional assumption because you want to make sure that the Hecke transformed vector bundle will also get an induced Higgs field. And that's the case if this condition holds, because then we can define the n minus k's fundamental Hecke transform of the Higgs bundle at the point V. And it is going to be this, this diagram will give it. So we will have the Higgs bundle here. We can restrict it to the point and then take it to the quotient to W at the point C, the skyscraper sheaf. then we will have, by your assumption, a map from this skyscraper shift to here, and then you can make this diagram commute uniquely with the Higgs bundle in the kernel. So E prime will be a subsheaf of E, which will be therefore torsion free, and therefore it will be a locally free sheaf as well. So this is the Hecke transformed Higgs bundle. So the proof goes by induction on the number of zeros, total zeros. We have the degree of the sum of these divisors, delta 1 to delta n minus 1. So if the degree is 0, that's the first step. That means because they are all effective divisors, they are all individually 0 divisors. In particular, it means that BI has no 0. And because everything is up to isomorphism, we can actually assume they are just 1, the identity. They will be a section of the trivial bundle. And then again, conveniently, we can choose the first line bundle to be trivial, the first divisor, the zeros divisor to be 0. And then this will give us what we call E0, the canonical uniformizing Higgs bundle. So that's somehow, we think of this bundle is at the very top on the nilpotent cone. And then the upward flow from this top element on the nilpotent cone is going to be another friend, is going to be the so-called Hitchin section of the Hitchin map. So the upward flow just agrees with the Hitchin section, and because it's a section of the Hitchin map, it implies that it is very stable. It will only intersect the nilpotent cone in a single point, namely at E0. And amazingly, Nigel already noticed this, that because of being a section implies it's a closed subvariety. So Nigel, in a sense, in the original paper in '89, I believe, he already noticed that it was very stable. And then step 2 is that we are going to apply Hecke transformations to the canonical uniformizing Higgs bundle. And the observation is that we can reach any of the type 1,1 Higgs bundles with a sequence of fundamental Hecke transformations at various points on the curve. And in the case when this divisor is reduced, there is no double point anywhere, we can actually do this by Hecke transformations at each of the point only once. And there, it's a very nice Hecke transformation, these fundamental ones. Basically, it goes through a Hecke correspondence, which is somehow has a properness property. And because of that properness, the closeness of the upward flows will be preserved. That's the rough idea. And in the case when the divisor is non-reduced, then you can use again Hecke transformations to produce what's called the Hecke curve inside the intersection of the upward flow with the nilpotent cone. So in both cases, it's very simple and very conceptual, at least for me, to understand why in this case you have very stable Higgs bundles, why the upward flow is closed, and why in this case the upward flow is not closed, why do you have non-trivial Higgs bundles in the intersection. And now let me finish with our original motivation of in the paper was to understand the mirror of these Lagrangians. So, okay, I already said you have this Bielanitsky-Birla decomposition into Lagrangian vector spaces, the union of Lagrangian vector spaces. And mirror symmetry is supposed to take a BAA brane, a holomorphic Lagrangian in the Higgs moduli space complex structure, into a BBB brane, which should be a nice, at least one, the simplest objects of BBB type should be hyperholomorphic vector bundles. In fact, we conjecture that the mirror of an upward flow will be a nice BBB brane, a nice vector bundle, hyperholomorphic vector bundle, precisely if they are very stable. So very stability controls the mirror to be just a nice vector bundle. And I show you what we can prove in this regard. So what we will do is that I will relabel these type 1,1 things. Instead of a vector of these divisors, I will record the sequence of Hecke transformations I had to make to get to this point. The way to do that is to have a map, a finite support map from the curve into dominant weights of GLN. And this is exactly the right formalism. And then you can translate such an information precisely into a vector of dominant weights for GLN. And we record the ones which are non-trivial. There are finitely many of them. And so instead now of labeling things with the vector of divisor, we'll label them with the maps to the dominant weights with finite support. And now we will say that E mu is very stable. Well, if it's very stable in our sense, but you can see nicely, very nicely, that exactly if the image of mu at every point when it's non-trivial, I can actually only do one of these Hecke transformations. It's a, what we say, it's a minimal element in the weight lattice with respect to the usual partial order on dominant weights. Namely, you want the difference to be a linear combination of positive linear combination of positive roots. That's the usual partial order. And then the minimal with respect to that, they are called minuscule, will be the ones, these are in the case of GLN, these are just these fundamental ones which we looked at. And the theorem, well, it's an easy, nice observation that very stable, the top points in that partial order is equivalent with the lowest point, the minimal point with respect to this partial order. So I don't know, is there a question now which is good to ask? I cannot hear you, Ron. Or maybe
there are a couple of questions, but why don't we move them to the question and answer session?
Let's do that. Okay, let's do that. Because we still have, I don't know, maybe 5, maybe a bit more minutes to be able to tell you the conjecture. First, the conjecture then. So it's in the very stable case. I promised you the mirror is supposed to be a vector bundle. And this is nice to say which vector bundle the mirror should be for the case of very stable upward flow. In that case, type 1 upward flow. So the conjecture is that the mirror, the structure sheaf of the very stable upward flow should be a tensor product of vector bundles, each of them cooked out from the universal Higgs bundle in the representation attached to mu ci. So we always have a positive, a dominant weight, and that will determine a representation of GLN. And then this is a GLN bundle, so we take it in that representation. I get a, okay, this one already was a vector bundle, but you get a vector bundle, you restrict it to the point ci, and then you do it, and then you tensor them together. And that's a nice vector bundle, and we will call this lambda mu. And so the theorems we can prove about this, first is that it is true on the generic fiber of the Hitchin map, in the sense that if I do Fourier-Mukai transform, I take a very stable type 1, upward flow, I intersect it with the generic fiber, I will get a bunch of points. The mirror, the Fourier-Mukai transform will be a vector bundle, and this will be precisely this vector bundle restricted to the generic fiber. Then we can also prove that this mirror, this is a really big restriction to be hyperholomorphic. It has this hyperholomorphic connection because of this universal bundle origin. Then the last thing we prove, which is that somehow the one which goes out of the usual things of looking at generic fibers, is that we can identify what should be the mirror always by on the Hitchin section by just pushing forward the structure sheaf. So what we can prove is that the push forward of the structure sheaf of a very stable upward flow of type 1 is a T equivariant vector bundle on the Hitchin base, which actually as a T equivariant vector bundle agrees with the conjecture mirror vector bundle restricted to the Hitchin section. So when you compare then these two T equivariant vector bundles, they will actually be just the same if they are the same T vector space over the origin. So we take over the origin, this vector bundle is a vector space, and it's a T equivariant vector space. And then here I have another T-equivariant vector space, but excitingly here we see the representation itself, or the direct sum, the tensor product of these representations restricted to the canonical Higgs bundle. And the T character does agree. And this is, I argue, is a consequence of mirror symmetry. So the upshot of all this was to explain that, in fact, and this is all retrospectively, we could have or should have started just looking at what Kapustin and Witten are suggesting, but retrospectively, I can see this as a consequence of what Kapustin and Witten are talking about, Taft operators and Wilson operators. But that would be another 5 or so minutes to have this discussion, or we can already have questions. What would be the best?
Let's make it your decision.
Okay, so then quickly I go through this, and then just to see how this one can be derived from ideas of Kapustin and Witten. Okay. So what they do is that they generalize, look at more general Hecke transformations than these fundamental ones, these minuscule ones in general. So what they argue is that for every co-character of the group, which is a character of the Langlands dual group, a dominant one, you will get precisely an irreducible representation of the Langlands dual group. To every of them, and the point C on the curve, you can actually define a Hecke transformation, which they call a Taft operator, which acts on, well, it gives you a correspondence which you can use to define a Hecke transformation on coherent sheaves on the Higgs moduli space. And this is a Taft operator. And then you have on the other side, you get a so-called Wilson operator, which is just tensoring with the universal bundle in the particular representation restricted to a point. So this is a nice vector bundle, the same kind of vector bundles we had before. And you tensor with this. This is Wilson operator. And then what they claim is that mirror symmetry should exchange the two, which can be formulated like this, that if you use mirror symmetry, and then W gets transferred to H mu. So now, usually everyone, or at least Kapustin-Witten and the geometric Langlands approach, thinks about on this side to apply this to a particular type of BBB brains, namely to structures, to skyscraper sheaves at points. And then you get these Hecke eigensheaves and all that story. But what we are looking at retrospectively is another canonical BBB brain, namely the structure sheaf of the Langlands dual Higgs moduli space. And now if you apply this conjectured identity on this side, you will just get this universal bundle at that point, in that representation at that point. So it's a very nice vector bundle and very nice hyperhomomorphic vector bundle. And on the other side, you first apply the mirror symmetry to the structure sheaf. Again, it should become the structure sheaf of the Hitchin section on this side. Now you take the Hecke transform of the Hitchin section, and its mirror then, at least we know what the mirror always should be restricted to the dual Hitchin section. It should be just the push forward of the sheaf itself. So we push forward by the Hitchin section of the Hecke transform, by the Hitchin map, the Hecke transformed Hitchin section, and that's what we are supposed to get. So we are going to get, according to the conjecture, the push forward of the Hecke transform Hitchin section should be this beautiful vector bundle on the Hitchin section itself. So when you restrict to the zero, you get these beautiful conjectures about what the T character of this push forward of the Hitchin section by this Hecke transform structure, the Hitchin section should be at zero. This vector space should agree with the representation itself. Now in this situation, I think that we are only doing Hecke transformation at a single point C. And then this thing actually is, of course, fundamental in the representation theory of the Langlands dual group. And this also turns out to be something very nice. It's the intersection Poincaré polynomial of the closure of this Schubert cell in the affine Grassmannian. So this is called, it follows from the geometric Satake isomorphism, but here we are proposing another geometrical understanding of the same. This is the representation of the Lagrange dual sign. And even more detailed, you can start to then think about how the representation can be seen on the Hecke transformed Hitchin section side in terms of these upward flows. And then what we can conjecture is that the Hecke transformed Hitchin section at a type 1,1 Higgs bundle, or the analog of this for the general G case with respect to this co-character, should be given this T character. It should exactly be this Kazhdan-Lustig polynomial, which is Lustig's T analog of weight multiplicity. So that's, for me, an exciting numerical prediction coming out of these mirror symmetry ideas. And here what we need to study more is these Hecke operators, which are much more difficult in the case when mu is not a minuscule representation, the ones we study in the paper. So very stability has to do with minuscule Hecke transformations. If it's not minuscule, the upward flows become not closed. You will have things above it, and that's where these multiplicities should play a role. And that concludes what I wanted to say.
Well, thank you very much, Tamas. Everybody, let's applaud.
Thank you.
We do have a number of questions, so let me ask Ashwin, Pavel, and Jan to unmute themselves. Ashwin, would you like to ask a question directly?
Yes.
Yes, sure. Am I audible?
Yes, you're audible.
Yeah, okay. So my question is there anything special about the very stable Higgs bundles of type 111? Are there very stable Higgs bundles of other types as well?
Right. So it's a very good question. I already started the very stable bundles were already proved by Lomond to exist. So very stable bundles give examples. So in the GLN case, Higgs bundles, fixed points of the cis direction are labeled by ordered partition of n. You have this chain of subline bundles, and the type n is precisely this component. So in that component, we know that there exists very stable Higgs bundles, but they are much more complicated. There, it's much harder to, that's the notion of what they call wobbly, the Ron and Tony. The wobbly divisor is very complicated. That was in fact the original motivation for Drinfeld, etc. But in between the two, there is a whole plethora of other type of fixed points. For every ordered partition of n, you have fixed points of the cis direction of that type. And then we don't know, honestly. We have a numerical invariant, which we attach to this, which was called here an equivariant multiplicity. And in the case of a very stable Higgs bundle, the equivariant multiplicity must be a polynomial. And that gives actually a lot of difficulty for a Higgs bundle to be very stable. And it turns out that some components of other types, like type 2,1, for example, some of the components, this multiplicity, which you can compute from an infinitesimal information, is never a polynomial. So you can deduce that there will be fixed point components which will not contain very stable Higgs bundles. This was contrary to my expectation, because rank 2, everything is type 1,1 or type 2, but in rank 3, some 2,1 bundles components will not contain very stable Higgs bundles. But it turns out that you can show that they are actually cannot be very stable precisely in the range where the numerics work. So we conjecture that in rank 3, this covers all the bad components, and we conjecture the other type 2,1 components to be very stable. But then in rank 4 and up, this even breaks down. So even if you have this numerical objection to be very stable, if you don't have it, then it still could be not very stable. And so therefore rank 4 and up, we don't even have a conjecture which fixed point components will contain very stable points. It seems a much more difficult question in between the two in the general case. And the reason we look at type 111 is what I try to explain here at the end, is that these are the ones you can achieve, you can achieve by using Hecke transformations on the Hitchin section. So it's on the tip of the iceberg. you start with the Hitchin section, you start to do Hecke transformation, you will get only to these type 1-1 fixed points.
Mm-hmm.
Somehow when you go to the other ones, you have to do something crazier. I don't know how to move between the two regions of 2-1 or other type of fixed points.
Thank you.
Pavel, do you want to go next?
Yeah, so I wanted to ask, could you comment on generalization to the parabolic case, and in particular in genus 0, maybe there is something simpler that could be said, let's say for GL2 or GLN?
So we haven't looked at that. So, but the general machinery works without. I mean, the machinery. So we have a notion of very stable Higgs bundle in the parabolic case. The same definition for any semi-projective variety. You have this notion. Then I mean, one has to study Hecke transformations in the parabolic case. It's slightly trickier because you have to worry about those parabolic weights and whatever. But I think that should be possible to be done. So I expect the same kind of results, that the type 1-1 case will happen there. In the genus 0 case, then it will be the fixed point components will be symmetric products of the curve, which is just products of Pn. So it's very simple fixed point components. And then I expect a similar big diagonal thing like here. So you have to throw out some sort of big diagonal. It should be very similar in that case, but because I haven't precisely, I mean, one has to, basically the question is, how do you do Hecke transformations in that case? If you understand that, I think these things should immediately generalize. We have a formula which, if you have very stable upward flow, we have a formula which computes the multiplicity of the corresponding component in the nilpotent cone. That formula is general again. So if you have a very stable parabolic Higgs bundle, you will get an infinitesimal formula, which just by knowing the tangent space at the fixed point, you can compute the multiplicity of that component. Mm-hmm. So rank 2 case, for example, it should be the same story. I think in rank 2 case, you will get all components will contain a very stable Higgs bundle, and therefore you can compute the components of the multiplicity of the components of the nilpotent cone, for example.
And the attractor sets in this case will be projective spaces?
The fixed point sets
yes.
of type 1-1. In the higher rank case, it's going to be product of, I believe, product of symmetric products of the curve, therefore products of projective spaces. In the rank 2 case, it should be a single projective space.
Mm-hmm. Thank you.
Hi, Tamas. So I have two types of questions. One is sort of similar to Pasha asked, but it's about irregular Higgs, which irregular parabolic Higgs, yeah.
So that's an interesting and a trickier question, because in the parabolic case, we assume the Higgs field to be nilpotent at the puncture. So that means the C star will still can act on those things. It will, the residue which is fixed, it's even C star, it still could be carry an action of C star. Now, for parabolic irregular bundles, it's trickier than that. In fact, there is a way to produce a C star action on the parabolic Higgs moduli space. It was considered in a paper by, I think, Gukov, Pei, maybe Nakajima. I'm not sure precisely who did that. And they have, you have to combine, it has to be on P1, because you have to combine the P1 action, right? When you have the residue, now it's irregular. You have this higher order terms, you multiply with C star. You have to do something on the curve to undo the action on the polar part of the connection. And in fact, you can do this on P1 if you have at most 2 irregular points, the fixed point, the 2 fixed points of the C star action, then you can combine these C star actions and you will get a C star action. Now, I don't know by heart if this is this satisfy the property of the weight one, I don't know that. If it does, then you have these Lagrangians, but I am not sure.
So it's no more than two irregular points, yeah, on P1.
You can have two irregular points on P1, then you can still construct a cis direction. According to Andy, it is still maybe. Oh, then if he says that the overflows are not Lagrangian, then they are not.
Yeah, but maybe it can be modified. So that was
I don't think you have more freedom. I mean, and anyway, I think here you just have to compensate by changing the polar part by cis direction. This actually is the only time. So when, okay, I started to think about these affine Grassmannians because this is what shows up, and that's actually how you construct these Hecke transformations for more complicated case. You have to look at the affine Grassmannian, and that will have two kinds of cis directions. One is the one which comes through the maximal torus. That's the kind of ones which show up from this cis direction. And there is this funny one, the loop through the loop, and that cis direction is the one which you can use for this particular irregular thing, I believe. But that's why it just was a comment that this cis direction, which should be relevant for your irregular Higgs bundles, has to come from this cis direction on the affine Grassmannian, this loop thing, and that's a different kind of animal.
Yeah, okay, I understand your point. And the second question, it's kind of I didn't hear what you said about the mirror symmetry in terms of Fukaya categories, because I mean I had my own class and I just switched off your sound. I saw that you wrote the Fukaya category, but I didn't understand what did you mean by that.
Well, this was the part, if you had listened to me, I would have hopefully said things like it's very schematic. Yeah. That was some sort of expectation. So that category is not defined mathematically. It should be the category of the boundary conditions in that A model, what the physicists are considering. It's not well defined. I don't think it's well defined mathematically.
Do you expect that it will be sort of a category of perverse shifts on the core?
Right. So then okay. So then what they do, I think Kapustin-Witten, for example, that they relate those things to the categories in the geometric Langlands correspondence, and there things are better defined. Maybe it's already well defined there. I don't know. Then I think there is a way to understand the Fukaya category. I don't know with which one. It's maybe the D modules, and then of course if you have a D module, then you can get something on the nilpotent cone, right? Then you will get it's a singular support. Yeah, I don't know. I don't know. That's the truth. But Fukaya category perhaps is best understood in geometric Langlands because their things are better developed.
Okay. Okay. Thank you.
Alexei, if you can unmute yourself, you're next.
Hi, thanks for the great talk. I just have a really vague question. So just because, Nakajima has a series of conjectures, how, 3D mirror symmetry, it relates, for example, to queer varieties of different dimensions, but there is some kind of interesting relations between fixed points on one queer variety and attracting varieties and some kind of coherent shifts on attractive varieties related to some part of the coherent and category coherent shifts on the other varieties. And it kind of looks similar to what you were saying. Is there any connections or?
Yeah, I agree. I have been, of course, listening to those kind of talks, but we noticed this, as I mentioned. We wrote the paper almost 2 years, and then at the very end, before putting it in the archive, we wrote a last section about further issues, and then we started to connect the dots. And so it's 1 month ago. So could be related. What I see is that it will be intimately related to the affine Grassmannian and the Schubert cells, the closure, the same business which I think does the 3D mirror symmetry. You will see the slice, it will play a role. But instead of somehow doing intersection cohomology, we do here more like T-equivariant coherent cohomology. But I don't, I mean, that I don't see, and then I don't know enough about the Nakajima story yet. So I am learning all this now, so.
Okay, so let's take a last question maybe from Sheriar.
Hi, thank you. I was just wondering if you know what kind of representation of the geometric fundamental group under non-abelian Hodge correspondence does a very stable bundle of parallel type 111 correspond to?
Could you slow down a little bit? So
Yeah. So just what would be the representation of the geometric fundamental group under non-abelian Hodge correspondence applied to very stable bundles of type 111?
okay, so I think the difference, so in the story I mentioned that if you look at this this thing by Kapustin-Witten, this identity, if you apply this to as a point on MDRAM, actually this one should be as understood on MDRAM. You know, and then then it's a point and MDRAM, then you get a flat connection, then you have a representation of the fundamental group. So if you look at this at the skyscraper sheaf, then it relates to there, but then you have these Hecke eigensheaves, and those are different animals. Here we are looking at, instead of a point, we just look at the structure sheaf. So every point in the MDRAM, so somehow we look at all the representations of the fundamental group at the same time. And we look at its the action of the Wilson operator on that. And on the other side, it gets translated by looking at the Hitchin section. That's where the structure sheaf will go to the Hitchin section under the Hecke transformation, and it's mirrored back.
I see.
So it's somehow not a single one, all of them at the same time.
Right.
Yeah.
So can you, so what is the thing on the right-hand side, the locus of flat connections? So this W mu that you explained.
Here I am in this classical limit in the language of Donaghy and Panther. So I look at everything on the Higgs moduli space, but these things originally, or actually for Kapustin and Witten, they make sense on MDRAM as well. So this one will act on, okay, maybe I make here. So this one can also be defined to act on the derived category of coherent sheaves on MDRAM instead of the Higgs moduli space.
Mm-hmm.
And that's, if you take here a single point, the structure sheaf of that, and then you look at this, then this is the thing which gives you the, so now you are interested in first the mirror of a point. The mirror of a point should be something which has to do with the fiber of the Hitchin map, some line bundle on it in this classical limit, and then you have to do some T-module stuff. And then you want to look at the Hecke transformation of that. And then this will actually, I think, tells you that that it will be a Hecke eigensheaf, I believe. But okay, this is not what I study. I wanted to emphasize that it's on the tip of the nilpotent cone that all things happen, and this one, the original one, the geometric Langlands, happens at the bottom of the nilpotent cone.
I see. Thanks. And a very naive question about the SYZ mirror symmetry, and I will just ask it in the case of elliptically fibered K3, just because I mean, it's a smaller dimension example and easier to understand. So if I have an elliptically fibered K3, I can apply the SYZ mirror symmetry to generic fibers, which are elliptic curves and not the ones which are degenerate. So then I get a new family of elliptic curves. And the new family's singular fibers are the same as the old family singular fibers. So does this imply that the monodromy that should, as you go around the singular fibers in the original one and the SYZ one, is that the same?
Well, it's not a Higgs bundle question, and I'm really certified to discuss Higgs bundles. But I don't know, maybe someone else can tell you if this is correct or not.
So this would translate to Higgs bundles question as well, that on the base, if you just look at if you remove the discriminant locus, then the base has pi1 and it has some monodromy. And one can ask how the monodromies of the two families compare.
Okay, so again, so you can do this kind of our kind of mirror symmetry in the case when sometimes, like what Pavel was asking, it could be a surface,
Yeah.
the Higgs bundle moduli space, and then you would be doing something that you are talking about. But yeah, but I mean, monodromies now I cannot say anything really authoritative. So.
Okay,
Thank you very much, Tamas. Maybe everybody who is unmuted can help thank you for the beautiful talk. And well, thank you. And we will reconvene in 2 weeks. Goodbye, everybody.
Bye-bye.
Bye.